Okay, so we're going to do a little introduction to right triangle trigonometry. And right triangle means this is trigonometry associated. You have to have a right triangle. And the basic idea for trig that you want to keep track of here is an application of similar triangles. Suppose I have two right triangles, and each of them has an angle of x degrees. What then can you say about these two right triangles? And the answer is yeah, they'd be similar. So if I have similar triangles by angle, the third angles will also, by no choice, or by pairs of corresponding angles and similar triangles are congruent, third angles will be congruent. So if I've got similar triangles, the key is ratios are the same. So for example, A over B would equal D over E. Or for example, A over C would equal D over F. So if I've got these ratios equal, now these are two triangles with an angle of x degrees. If I had, obviously there are infinitely many triangles that have an angle, right triangles with an angle of x degrees. In all of those triangles, these ratios, if I set up ratios of corresponding sides, they're going to be equal. Now we've looked, for example, at 30, 60, 90 triangles and 45, 45, 90 triangles. And for the 30, 60, 90, we knew that opposite the 30 was x, opposite the 60, and if I have a 30 and 90, that will be 60, is x root 3, and 2x. And for the 45, 45, 90, I have x, x, and x root 2. So if I look at ratios of corresponding sides here, for example, I would have another 30, 60, 90 triangle, which would have, say, maybe a sides of, say, 4 and 4 root 3 and 8 for my 30, 60, 90. And if I look at ratios of corresponding sides, clearly x to 4 has to equal x root 3 to 4 root 3. And also then if I use and simply rearrange that ratio, I would have x to x root 3 would equal 4 to 4 root 3. And in general, thinking about that ratio of sides in a 30, 60, 90 triangle would be something like x over x root 3. And that, we did a homework problem on that. That might simplify to 1 over root 3. Or x to 2x would equal 1 over 2. And again, look at if you do it with numbers. I've done it here with just our basic x, x root 3, 2x. I can also do that if I've got a 30, 60, 90 with specific numbers. 4 to 8, certainly there's my 1/2. 4 to 4 root 3, there's my 1 to root 3. And I can obviously do the same also with my 45, 45, 90 triangle situation. X to x root 2, that's a leg to the hypotenuse, equals 1 over root 2. And if I don't like square roots in the denominator, I can get root 2 over 2. That's the ratio of a leg to the hypotenuse in all 45, 45, 90 triangles. Ratio of a leg to a leg is pretty simple. That would be x to x, which equals 1. Well, of course, the ratio of x to x is going to be 1, so that makes good common sense. Okay, so again, knowing that those ratios in any right triangle with a certain degree angle, call it x degrees. If I have a right triangle with an x degree acute angle in it, then the ratio of sides, say A to B, will be the same in all right triangles that have an acute angle of x degrees. So we then are going to set up by definition and give names to some of these ratios. And for now, we're going to look at 3 ratios relative to an acute angle in a right triangle, and they're called the sine ratio, the cosine ratio, and the tangent ratio. And they have abbreviations, SIN, COS, and TAN. So if I want to talk about the sine of angle A, by definition, the sine of an acute angle is the length of the leg opposite that acute angle divided by the hypotenuse, and that's an A over C. We then notice that the or we then define the cosine of an acute angle is the ratio of the adjacent leg, and the adjacent leg is the leg that forms that acute angle. Notice the hypotenuse and a leg form an acute angle. The cosine ratio is the length of the leg that forms the acute angle over the hypotenuse. And finally, the tangent ratio of an acute angle is defined to be the ratio of the opposite leg over the adjacent leg. Now, could I define the sine, cosine, and tangent ratios also for angle B? Sure. The sine of B is going to equal opposite leg, which is B, over hypotenuse. The cosine of B is going to be the adjacent leg over the hypotenuse. That would be A over C. And the tangent of B is going to be the opposite leg over the adjacent. And the last thing to notice here, are there some relationships between the sines and cosines and tangents of the two acute angles in a right triangle? Do we see some relationships here? And I'll let you think about that as you do your homework and as you do your reading. Now, in terms of keeping track of these definitions for trig, my recommendation is you keep track of them as opposite over hypotenuse. You're thinking, you've got a picture in your mind, you see an opposite leg over the hypotenuse relative to an acute angle in a right triangle, and you know that is your sine ratio of whatever that angle is. And you know that adjacent over the hypotenuse is your cosine relationship, and that your opposite leg over your adjacent leg is your tangent relationship. And that's how I recommend to do it. Keep track of those definitions visually. Now again, mnemonic devices are always good, and some, historically, students like a mnemonic device. The one that certainly has been around for a long time is you've got some king with a weird name, SOHCAHTOA. King SOHCAHTOA is the king of trig ratios, and that helps you keep track of, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Frankly, I find that more difficult than just keeping track of opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. But again, if you want to come up with a mnemonic device, there's one that's been used in the past. Now, how can trig be useful in addition just an abstract sense of finding some links or ratios in a triangle? Let's suppose I'm standing here at point A, and I see this building over here, which I'll assume is perpendicular to the ground, and I'm interested in how tall that building is. Now, I know that I am 50 feet away from the base of the building, and I can measure up, I can eyeball up, and actually form an angle with the top of the building of 17 degrees from where I'm standing. And I want to find, obviously, the height of the building is h. And so from that specific application setup, I simply have got a trig ratio in a right triangle with one acute angle of 17 degrees. And in terms of what I'm given for information, I'm given an adjacent leg and an opposite leg. Those are the things that I'm interested in, that I have information about or want information about, and relative to the acute angle of 17 degrees. So knowing that I've got an opposite leg and an adjacent leg, I then can set up, by definition, the trig ratio. The tangent of 50 degrees is h over 50. If I want to solve that for h, one arithmetic step, 50 tangent of 50 degrees equals h. Now I could leave that as an exact answer, or I could take my calculator, making sure I'm in degree mode, which we talked about in class, and simply find a decimal approximation by punching some buttons in the calculator. Okay, last bit of information here as you go on. Generally, and this will come ahead in trig class, if you're given a triangle and say you've got sides of F, G, and H, convention says that you can label the lengths of the sides as little h, little g, and little f. So you might see that that lies ahead in terms of just how to label a triangle if you're doing some of the right triangle trig. Capital letters for the vertices and small letters for the sides. And the last thing, again, that I want to have you keep track of is it's a remember thing. It's what are trig values? And the answer is they are ratios. A trig value is a ratio. It was, as we saw, a ratio of lengths. It was an opposite leg over hypotenuse. That's a ratio of lengths. Now I can express that ratio as a decimal. And if you look at a table of trig values in your book, or you take your calculator and find tangent of 28 degrees, it's going to give you a decimal. Yeah, but that decimal is coming from a ratio of lengths, and it's a decimal approximation to an exact value. And so when I'm looking at something like tangent of 28 degrees, what comes to mind is that is a ratio. It is, for tangent, it's going to be the opposite leg over the adjacent leg in a right triangle relative to an acute angle. So one value, I don't have two things. I don't have a tan and a 28. It's the tangent of 28 degrees, and it's a ratio of two lengths of two sides in a right triangle.